Hello, everyone. This is the 9th LightOn AI Meetup, and I'm very happy to present Sara Hooker from Google Brain. And she's going to give a talk about the hardware lottery. You probably have heard about it. And if not, you will hear about it now. So, Sara, you can start with your presentation. Thanks.
Thank you, and thank you for the lovely invite. It's nice to be here and to be talking about this. Perhaps Jacopo kindly suggested that some of you may have heard of the hardware lottery, but today I'm hoping to really talk about why it matters, and in particular, what do we mean by hardware lottery, and what does scientific progress look like within computing? So a little bit of background about me is that my research agenda to date at Brain has focused on training models that fulfill multiple criteria. So this can be compact models to deploy in resource-constrained environments, or fair, interpretable, robust. And in many ways, what I'll be talking about today is not particular to any of these subtopics, but it's really about how does research make progress and how in a marketplace of ideas do we evaluate the quality of research ideas. And I think most people acknowledge that there's noise in the marketplace of ideas, so we don't always identify what is the most promising idea immediately. And in fact, there's inertia in how we make scientific progress. But what's interesting is that in terms of machine learning research, researchers tend to talk a lot about certain types of noise. So we talk a lot about the peer review system, which we're quite grumpy about because the amount of submissions has spiraled, and that has reduced or created more variance in the quality of reviews. We talk a lot about access to compute, but we don't specify what type of compute. And we talk about funding to secure research independence. And these are all important types of noise, but I think what I'm going to suggest in this talk is that critically, they're not comparable to something which dominates and has dominated computer history progress. And that is the noise introduced by our toolings. You see, a researcher in machine learning today typically develops a research idea on a single type of hardware and with an optimized software stack for this hardware, and largely abstracts away the hardware and the software from the consideration of the idea. In fact, even in compression research, where I frequently contribute, we typically even there use metrics which are centered on the theoretical properties of compression. And there's far less work on connecting how our compression algorithms actually deploy to all these different environments. And so at present, we largely decouple software, hardware, and algorithm and abstract away software and hardware. And what I'll argue today is that this is a mistake, because history tells us that hardware and software have been the deciding force in many of the big swings in which ideas win and lose. And to lay out essentially the evidence that suggests that this is the case and that we should care more, we first have to ask, why have we abstracted away software and hardware? What has incentivized the development of these communities in isolation? And what is the implications of this silo development? And this is really what I coined the hardware lottery, which is all the ramifications of us treating these as independent variables rather than highly interdependent. But I do want to end by talking about why this matters and why the advent of domain specialized hardware in fact makes the winners richer and the losers poorer. And then I'm hoping to leave plenty of time for questions and discussion, because I always enjoy it when I'm talking to an audience that has a mixture of backgrounds and domains. And so I hope that there'll be plenty of engagement there. And to begin with, though, I wanted to provide a little bit of context about how do we get here. So why is our workflow like this today? And in fact, if you look at very early computer science history, it wouldn't be apparent that this is the case, because in early computer science history, the machine was the algorithm. So Jacquard looms, Charles Baggage's analytical machine, the first Mark I, Mark II, these were all both algorithm and computer. They were built for a very narrow purpose, and this was largely determined by the cost of electronics and the lack of portability of software. So it was very difficult to recode. So once you coded something, it was done. And while this was driven by necessity, an important framing point for this conversation is that our own intelligence is both simultaneously algorithm, hardware, and software. We don't move our brain algorithm to different brains over the course of our lifetime. In fact, the word brain is synonymous with thinking about both our thought process as well as the hardware it runs on. We can't help but summon up an image of what our brain is like. And the reason why this is interesting is that in many ways, what followed this early period of very specific specialization was a radically different period in computer science history. And it was a period in which the way that we make hardware, as well as the way that we engage across these communities of software developers, hardware research, and machine learning research became entirely different and became very siloed. And the motivation for this was the general purpose era, which really changed the economics of the cost of information. So in 1969, Moore published a piece which was very aptly and succinctly termed cramming more transistors onto circuit boards. And as self-evident in the title, a lot of what Moore is saying is that he predicted that by essentially making circuit boards more dense with more transistors, you could change the economic trade-offs of transforming energy into information. This prediction was self-fulfilling, although he initially did it as a marketing ploy to push the sale of transistors. But it was self-fulfilling, and it led to a predictable increase in compute and memory every 2 years. And why is this important? This is important because it made hardware design risk adverse. The emphasis shifted to universal processors, which could do a myriad of things. Perhaps the best example of this, of course, is CPUs. But it really prompted that move because it was very hard to justify experimentation when there were predictable profit margins. It's the same way in machine learning research, how over the last decade, we've largely focused on variations of deep neural networks. And only now are more exciting, interesting, riskier directions of research coming out, because when there's a feast, it's very hard to recommend diverting from the feast and exploring unbound territories. And the second reason, which made it hard to justify interesting exploration, was that if you were to invest a lot in a new design, it could be easily eclipsed by predictable increases in efficiency. What this meant is that in many ways, we became quite conservative, and it was very hardware designers largely optimized for the most general purpose software, which meant that researchers had far less reason to engage because they couldn't control any of the levers that impacted design. Of course, there were some limited deviations from this. So Thinking Machines was a great example of a startup which attempted to do things differently. But Thinking Machines is also very representative of the dependency on long-term funding. A lot of their funding came from DARPA, and when that dried up, so did Thinking Machines. And other than that, it was very specialized to certain narrow use cases, like chess, where the prestige of beating a human adversary attracted corporate sponsors, to certain weather use cases, or finance, where there was enough of a return to experiment with certain types of optimization. But by the end, and by the end I mean up until very, very recently in the 2000s, there were very few levers for researchers to guide the development of hardware. And this impacted how these communities trained specialists, as well as how these cultures evolved. So training became specialized for each of these communities. If you do a PhD in machine learning, you're unlikely to gain the domain knowledge needed to know what exactly your hardware is doing, or how to have an informed opinion about how you want your hardware to evolve in conjunction with your algorithm. But also the culture is very different. So hardware, in particular, because of the cost of iteration, is a much more closed culture than machine learning research. And in machine learning research, essentially, you've evolved towards a very unique open research culture. The number of publications has grown exponentially over the last 30 years, whereas hardware publications have stayed remarkably constant. And this all has implications for how ideas are evolved, but also the cost of engaging. And this is critical because a large reason why researchers began to treat hardware as a sunk cost to be worked around is fairly rational. So if you cannot impact something, or if it takes a huge amount of effort to impact it, it's far easier to abstract it and to hope that it has no implication on the merit of your idea. And of course, this is not quite the case. In fact, what I will argue is that hardware and software have had huge implications for the speed of iteration in computer science. And by ignoring it, we're actually ignoring one of the most pivotal factors that determines the pace of innovation. And this is what I term the hardware lottery. And it's that a research idea wins because it's compatible with available software and hardware, and not because it's superior to alternative research directions. And what I argue is that this compatibility, more than any other factor, has explained the speed of progress in computer science. Not what has progressed, but the speed of progress. And there's examples of early hardware lotteries. So Babbage was the creator of the analytical machine. And in many ways, this is a great example of being too early is the same as being wrong. One of my favorite quotes from Silicon Valley, the TV show. And really, it's a fascinating example of the materials needed. So Babbage developed the analytical machine, but didn't have the parts with the mechanical precision to make it during his lifetime. It ended up only being feasible with World War II, almost a century later, when transistors, which were being repurposed from radio, made it more feasible to make these type of computers with this type of precision. But a lot of what I talk about when I talk about the hardware lottery is the lost decades. So really the gap between when the algorithmic components of deep learning were already in place and widely accepted, and the empirical evidence that switched everyone to accepting this as a promising research direction. So the algorithmic components for deep learning were in place largely by the late 1980s. In fact, backprop was reinvented 3 times, and convolutions came in by combined with backprop in 1989 with the Jan LeCun's paper. But there remained a huge gap. And during this gap of 3 decades, deep learning remained a fringe discipline, much like we view the poor causal analysis and Bayesians today, because there lacked empirical evidence that this was a promising direction. And there also lacked consensus that this should be invested in. And why? I'll argue it's because of both incompatible hardware and incompatible software. So the first is that universal processors were very poorly suited to deep neural networks. CPUs were hard to parallelize because they were designed, in fact, to be generalizable. And this this meant that they weren't optimized for the matrix multiplies that dominate deep neural networks. There was a need to save intermediate results, which resulted in high memory overhead and low flops. So quite simply, the blocker was training networks that were deep enough. And this turned out to be key, combined with distribution of training. And the need for this was pointed out very early. So in the early 1980s, there was already consensus that hardware was needed that supported parallelism. And despite efforts in the 1990s to start thinking about this type of parallelism, they were short-lived. So they tended to be from academic research labs and didn't have the capital or to sustain exploration. Often they over-catered to the software language at the time, which was Prolog or Lisp. And so the actual obstacle became the difficulty of adapting both the software and the hardware to work with deep neural networks. And the interesting thing is that our breakthrough in 2012 was largely a hardware fluke. So GPUs were developed for video games, and in the 2000s, it largely became an accidental discovery. A lot of the early papers in the 2000s were trying to figure out how to adapt GPUs at a software level to work with training. But this was accidental in itself because GPUs were never designed to work with deep neural network training. And the key benefit that GPUs brought was that they were very good at the parallelizing matrix multiplies. And it was this that led to the breakthrough that many of us know in 2012, where for the first time, convolutional neural networks outpaced considerably other tasks, and overnight everyone switched to convolutional neural networks for computer vision problems. And this paved the way for significant research over the last decade in using deep neural networks for a variety of tasks and new architectures. And it's important to note, as I mentioned, that even hardware cannot be seen as independent from software. So software was also disadvantaged deep neural networks, mainly because software and what was widely expected of AI researchers who were training and doing PhDs in the day was that they learn either Prolog or Lisp. And both these languages were very well suited to connectionist networks, in particular to the type of algorithm which we now know as expert machines, where you have a series of logical if-but statements, and it's meant to encode human knowledge and then update based on some learning parameters. But these were not well suited for the type of essentially connectionist approaches that deep neural networks proposed. Oh, I think I said connectionist for the first, so symbolic approaches versus connectionist. So only in the 1990s or early 2000s did frameworks start to emerge. And you may know some of the latter ones, but some of the early packages were from MATLAB. There was Lush from NYU. And now we have PyTorch and TensorFlow. But this can be seen also as independent because in particular, the few deviations in hardware development that did occur in the 1990s often over-catered to Prolog and Lisp, and ended up, the hurdle became trying to make these languages work with deep neural networks. And this is perhaps the most interesting part of what I'm going to present today, because it's really what motivated me to write this paper, which is that we have this second pendulum switch back to specialized hardware. And this is driven by a few factors, many of which you may be familiar with, which is the end in Moore's law and Dennard scaling, spiraling energy costs of training. So particularly almost our insatiable appetite for bigger is better with deep neural networks means that we're frequently running into training costs of multi-million dollars. And the third, which is perhaps most pressing and what has really spurred a considerable amount of investment, is the widespread commercial use cases of deep neural networks. So there's no doubt that there are many use cases which are currently not being satisfied because there's incompatible hardware. This is really what has motivated my own research on compression. How do we make some of the algorithms that we have developed more accessible in many different types of resource-constrained environments? And this pendulum swing towards specialized hardware is really focused on domain specialized hardware, which optimizes for certain operations particular to networks that gains efficiency. So the types of domain specialized hardware we've seen so far tend to be optimizing for matrix multiplies further, but have also experimented with things like different types of precision, which may save on efficiency, but are very specific to the network being trained. And the question becomes, does this end the hardware lottery? In many ways, my narrative so far is that general purpose zero is what led us to these siloed types of communities. So does moving back towards specialized hardware, which involves a lot and prompts a degree of co-design, does it end this problem? And in fact, I would say it may make it worse. And the reason why is that specialized hardware makes it more costly to deviate from the beaten path of research ideas. It raises the cost of portability of code across hardware, and it increases the pressure on software to keep up. So this is a compounding cost because there's an ever more formidable and heterogeneous hardware landscape. And this in itself means that researchers are much more likely to stick with a type of hardware which is specialized for the ideas that they've been doing, rather than experiment with hardware that may work better for the ideas they may currently have. This is a very precarious factor because, in fact, it raises the question of how much researchers will implicitly overfit to making the ideas work on hardware that they have, rather than just working on the best idea. And a good example of this is capsule networks. So I love this paper. This is a paper that came out recently. It's called Machine Learning Systems Are Stuck in a Rut. And they look as a case study capsule networks. And capsule networks are a good example because in many ways they're trying to do something different. Capsule networks were a grumpy response to convolutional neural networks, and they're trying to solve some of the issues that researchers know exist with convolutional neural networks. And they do this by having a very different type of architecture. There's squashing operations that mean that it's not just a feed forward pass and a backward pass. And this turned out to be entirely incompatible with any type of either domain specialized like TPUs or GPUs. In fact, the authors had to run it on CPUs. And why is this interesting? It's interesting because in many ways, while this may not be the next breakthrough, it's a good example of how as soon as you change one notion of how we do things currently, which is to have all examples treated equally, we do a full forward pass for everything, we do a full backward pass for everything. As soon as you deviate from that and try a slightly different setup, you immediately run into problems. And that's because our hardware is overfit to the notion of a known batch size and a known set of operations that don't change or won't be altered depending on the inputs. And this raises the question of what are the failures we still don't have the hardware to see as successes. Because in many ways, this presentation is only possible after the fact. We have this huge counterfactual problem of we don't know the search space. So we don't really know all the failures that we've just decided are failures. But with the right hardware, it could have been much more promising. I think I've talked about this, but I think really what this is suggesting is that the winners are getting richer and the losers are getting poorer, because if your network or your idea does not work on current hardware, it's likely only to become harder to empirically show that it works. Now, I think it's important to recognize that the risk of this and how much importance you attach to the risk of this depends upon where you position yourself in an ongoing debate in the machine learning discipline. And this debate is really a question of, does symbolism still matter, and does prior still matter? Because actually, I don't like the word symbolism, but do we need priors about our data, or do we just need more compute and more resources? And this debate is kind of epitomized by these two excellent blog posts I suggest everyone goes to read. So we have the bitter lesson by Rich Sutton, and then Max Welling has this fantastic blog post, do we still need models or just more data and compute? And what Rich argues is that, in fact, he suggests that what history has shown us is that no amount of feature engineering, or you can more generally frame this as priors, where we impose some presumption of what we believe the function space to be, no amount of that will overcome the empirical success of just throwing compute at the problem. And in some ways, if you were to narrow your scope to deep neural networks, that's true. I mean, in fact, we're perhaps showing that's true. Like in many ways, by unlocking it with more compute, we've allowed for the scaling of these networks. And even now, empirically, it still holds that the more parameters you throw at the problem, the better it appears to do. Max Welling takes a different approach, and I really do recommend you take a look at this blog post. But what he argues is that the prior still matters, and your assumption about the data distribution still matters, because in many ways, there are many circumstances where we don't have a good, we can throw parameters at the problem, but it may be very costly to do so. And in fact, I hold this view. I think that currently the way that we're throwing parameters at the problem is in a regime where it's not clear we're ever going to get to the type of human level intelligence that we want to emulate and we want to transfer to machines. And that partly rests on the fact that it's almost as if currently, if we were to take the Rich Sutton approach, we'd be throwing so many parameters on the problem. It's like building a ladder to the moon. There are just enough things which are clearly inefficient about the way that we're building models that suggests we need a different combination of hardware, algorithm, and software. And some of these are also in what we currently do different from our algorithms. So deep neural networks have shown a remarkable ability to learn a narrow task, but there are critical things that are obstacles in terms of translating that to a more general form of intelligence, such as deep neural networks do not transfer well to new tasks. There's catastrophic forgetting. Humans have much more efficient hardware. Our brain runs on the energy of an electric razor, whereas our current models are ballooning in cost. And we do this in part because we have very efficient pathways. So for example, me walking and talking is very easy compared to me walking and reading. There are pathways which have been heavily optimized for certain operations. We have severe constraints on information. So we see in log scale, it takes a noticeable change for us to register. And we largely simulate what we see. So we don't do a full forward pass of every input. We in fact largely do a shallow pass and then check if there's anything surprising, and then largely simulate. So unless there's a noticeable change in your environment, you're probably not really seeing what is happening. And all that saves an incredible amount of energy. And it's all things that we don't do with deep neural networks. We treat every example equally. And so that means every example has to be seen the same number of times. And all this, to me, suggests that by removing these priors, which restrict the function space, we are taking a very inefficient path, and it will be very costly. And that leads me to err more on the side of we will probably need different combinations of hardware, software, and algorithm. Although, of course, this is moving history. So it is a little bit cheeky for me to say it, but I do think it's the most conservative approach to thinking about how a field can evolve, is to assume that your hardware, you don't want to lose degrees of freedom at the hardware level, because then you're backed into a corner in terms of what you can do. I want to end, and then I would love to open up for discussion, talking about the way forward. And the way forward is really a question of, is it possible to reduce the cost of hardware lotteries? So hardware lotteries will never be eliminated. There's always some inertia in terms of how we think about how these pieces come together. The same way that noise in the marketplace of ideas will not be eliminated. But it is interesting to think about, is it possible to reduce this cost? Do we have to wait 3 decades before we stumble across a hardware and can repurpose it? And in many ways, this question amounts to asking, how do we reduce the cost of exploring different hardware, software, algorithm combinations? So right now, it's extremely costly to explore different types of hardware because of the cost of iteration. So typically, developing hardware costs more than, it's around $165 million. And it's very costly in terms of also the iteration speed. So one reason that domain specialized hardware has kind of optimized for already well-known architecture developments is that you want your hardware, after all this investment, to have longevity, to be around for 3 years and recoup the costs. This makes what we encode in hardware in terms of domain specialized very, very conservative. Typically, the types of design features that are being encoded are already widely accepted research ideas. So for example, I work on compression, and one thing I would be really excited about is hardware that tolerates unstructured sparsity. And there are many clever architects thinking about this, and I believe that within, there are already some hardware types that are doing it, and I believe that this is an achievable goal, mainly because it's widely accepted as something which is feasible, but also it's commercially a clear attribute. To have unstructured sparsity, you arrive at lower levels of compression. Where there's not consensus, where the value of an idea is not already known and established, it's an entirely different conversation. And it's very hard to justify developing new hardware for an uncertain idea. This in part means that researchers need to be better informed about the implications of hardware on their algorithms. So we need to have a more nuanced opinion about what hardware we use and where. And that's what's going to improve the discourse around this. And this gap is, I would argue, largely a feedback loop gap. So currently, when I deploy to a certain type of hardware, and then I deploy to another, it takes several days. I have to redo my code. If I were to change from GPUs to TPUs, there's certain operations which are specific to TPUs. I have to then it's not an automatic deployment. And then on top of all of that, it's very interesting because what we find is that we don't have a good way to do this at scale. So for example, if I care about deployment at the edge, for me to deploy to actual cell phones or to deploy to different types of hardware that leverage things differently is considerable time. And it's out of my current research development workflow. The second factor is really that we don't have a national conversation about hardware that really talks about it in terms of how do we sustain long-term investment. So this this conversation cannot belong to only researchers. It has to come from a dedicated resource allocation about what types of hardware do we want to explore. This is particularly true for more innovative types of hardware, like biological hardware, where we try and think about using cellular level biology to encode different types of functions, or quantum computing, or perhaps some of the more risky forms of hardware development that entail unclear returns. But the third is really that there has to be a renewed effort on joint training and shared research venues. This is particularly tricky because there are still quite valid incentive structures for hardware being more closed form. But it's necessary, and this again is perhaps a priority that has to be set at multiple different levels. But until there's a joint vocabulary, which there currently isn't, I think if a hardware specialist reads a machine learning paper and a machine learning paper reads a hardware paper, there are many terms which will be puzzling to both. Until there's that, it's very hard to have a precise conversation. And scientific progress is all about having more precise conversations about how to push things forward. And so having these joint collaborations is very important in terms of calibrating what are important questions in each field and how can we collaborate together. I'm going to end it there. I'd love to open up for questions. On purpose, I left plenty of time for that because I would also, it doesn't have to be just questions. If you have an opinion, grumpy or not, please share. I would be happy to engage because I think part of the beauty of these type of meetups is that it brings across these cross-disciplinary perspectives.
Thank you, Sara, for the presentation. And yeah, I forgot to mention it at the beginning, but yeah, if you have any question, you can unmute yourself or write them in the chat and I'll ask them. We have one from Pierre Gutierrez. He's asking about unstructured sparsity you mentioned before. He asks, can't FPGA handle unstructured sparsity?
Yeah, it's interesting. There is work recently which is trying to illustrate this, but it's not. I think there's a difference between that and productionizing it so that it's works at scale for many different types of sparsity. From my understanding, the biggest tricky part right now is making it efficient when you fold in backprop as well. So you can do unstructured sparsity, but it's harder to combine that with a backpropagation layer. But perhaps Pierre knows better about the state of the landscape. Yeah.
Yeah, his comment was really not an expert here. So yeah.
Yeah. Okay. Do you know Pierre? That's funny. No, you're like, he's really not an expert. One more point I'll say there is that NVIDIA just came out with an early version of tolerated sparsity, so it is actively on people's minds. This is something which I would say is the difference between what I term a hardware lottery and what I term a short-term pain point. Like there's consensus amongst all researchers who work on compression that we want unstructured sparsity. And so there's also consensus amongst most hardware architects that we should try and get it. The question is at the cost and also how to make that, how to make it work. But those are solvable problems. So I think that is less, in my mind, I see that as something which is going to be addressed within the next 2 generations of hardware. The big question when I talk about hardware lottery is, what about the problems that we don't have consensus on? So someone proposes a brilliant problem and a brilliant solution to a problem, but we don't have the hardware to show it. Does the idea just get lost? I think in our current research framework, probably.
Yeah, thanks. There is Laurent, who is the CTO of LightOn, that wrote a comment, but maybe he can unmute himself and say it, or I'll do it.
You can do it, Jacopo.
Okay, yeah. Yeah, I was pointing out about unstructured sparsity that actually it's a bit the genesis of LightOn. Like the idea behind LightOn is born out of the compressive sensing field, where like we deal with compressing data that are sparse and so on. And so he's saying that we would be happy to discuss this offline, and we are very much open to a collaboration. So,
Yeah, absolutely. That's a lovely comment.
Are there any other questions? Otherwise, I have some.
I do have one actually.
Yeah, go ahead, Julian.
Hi, Sara. First, thanks a lot for this talk. I think this, in general, this idea of the hardware lottery is super interesting and puts into words a lot of trends in machine learning. I actually have kind of two questions. I have a first one, which is, so you mentioned that hardware lottery are not unique to machine learning, which is, yeah, it's very true. But have you seen in the research you have done examples of other fields overcoming the hardware lottery? So kind of finding a way not to entirely solve the issue, because maybe that's impossible, but maybe a way to alleviate the hardware lottery in other fields. Have you seen that kind of stuff?
So it's very interesting. There have been some examples mentioned to me, but the way they've been mentioned is anecdotal. So I'd be curious to hear other opinions. But the two fields that have been mentioned to me are astronomy and physics. So both have been backed by fairly aggressive national investment. And so there has been, and also the necessity of having particular precision on the inputs. So for both astronomy, the difficulty was the input data is often not recognizable. So it needs specialized hardware in order to have the degree of precision to make progress. So there was a clear understanding that current hardware wouldn't work. And I believe this is what informed the impetus for development, just how bad the current tooling was, which is always a good thing. I think the hardest part of iteration is when we're comfortable, because then it makes us scared to switch. But in astronomy, I believe one of the forcing factors was how bad imaging equipment was for their particular type of input. For physics, I think the anecdotes I heard were more along the lines that there was a clear international collaboration structure for sharing the costs of resource development. But this is more anecdotal. I do think in terms of what I imparted for those conversations, it seems that right now, the ecosystem is very private sector driven. So we have startups who are doing a lot of innovative things. We have big companies who are now taking on doing specialized hardware. But there's very little vision at a national level for how to do hardware. And this tends to mean that commercial use cases get prioritized, which means, again, that more risky approaches, which might have long-term benefits, the flukes, the GPUs, so to speak, are under prioritized. And this does have ramifications.
Okay, thanks a lot, yeah.
You had a second question, or?
It's more for discussion, so I will ask it maybe.
Oh yeah, please share.
But I will ask it if other people have questions that are clear cut. I will let them ask them so that we can move to maybe a more discussion format later.
Yeah, any other question?
Yes, maybe I have a question.
Yeah, go ahead.
Hello, Sara. Thank you very much for your presentation. It was very clear and resounding. So first, I work for a company, and I work with hardware people, and they work with languages that are hard for them to implement very fast designs. So for instance, if I want to do an addition, it's very easy to do it in software, and maybe in 5 seconds. But if I have to do another in hardware with in a hardware design, it will maybe take me like 15 minutes to do so. So the question is, there is no for the moment, the use of high-level hardware language in lots of big companies. Do you think it's we are going in the right path by using those languages, or maybe we have to use something else? What do you think about that?
Yeah, this is very interesting actually as a question, because it's really getting to the fragmentation issue of software and hardware. So I think there's a challenge right now where we have a much more heterogeneous landscape of hardware, but the way that we compile on hardware, as well as the high-level software, it's harder and harder to keep pace and make it optimized for different types of hardware. I don't have a good solution to this. What I can only speak to is the trend, which is software is also becoming more specialized. So there's much more investment in a given hardware and a given software stack. This also has implications for portability. So right now, I did mention the example, if I want to port over from GPUs to TPUs, I face certain obstacles. I have to spend a day or so recoding my code. But this is even harder if you think of something which is not as well used or maintained. Yes, you're correct. This is an open problem, and it will mean that software will itself become a much more specialized discipline, I suspect.
Yes, thank you. Just maybe, just I want to add that lots of hardware companies are trying now to use what they call SDK, and so it's easier for software developers to transform software design in hardware design. I would just want to take Mipsology, which is a company that does FPGA, and so what they've done is they say that for like machine learning engineers, they just have to transfer TensorFlow models into their FPGA cells. So it's easier for them. And the last example is maybe GraphCore. GraphCore that does what they call IPU, Intelligence Processing Units. And so what they do is that they transform calculus topology into graphs, and then they implement that in hardware systems. Which is very specialized, but at the same time, they keep software developments at high levels. So
that's very interesting. There is some efforts I know to do, or I guess to apply machine learning techniques to figure out how do you automatically compile tailored to different hardware. So you would do almost an automatic compiler approach where you're trying to understand, remove the tailoring, handcrafted tailoring component. But that's very interesting.
thank you very much.
Thanks. Any other question?
Yes, I have one. Hi, Sarah. Thank you for the talk. It was very interesting. Over the course of the past 30 years, we've seen initially an increase in demand for more accuracy in computing, and therefore more precision in terms of how numbers are represented. Nowadays, everything is going back into the different direction, more likely to much lower bits type of representation. Do you have a feel as to where this is going? I mean, we all know what is actually going on with the GPUs and everything, but do you see a trend there out of what you've been looking at? Or do you think that somehow we're going to be stopping at 8 bits, mostly because for those large machines, because that's what people think the sweet spot is? Do you think that we can go below this? What have you seen?
So I think it's going to be very task dependent. I don't see any reason we have to stop at 8 bits, because there's some tasks where we don't need high levels of accuracy, right? So really with these quantization approaches, we're seeing that we can drastically curtail the representation and still have a usable model. But we tend to fixate on preserving accuracy, as you said. So right now I work in compression, and the whole goal is maintain accuracy for a given level of quantization or compression. But the truth is, when you move outside the world of research, which is very focused on we don't want to lose anything, you realize that most real-world problems tolerate a drop in performance if it makes sense. So, for example, if your whole goal is just to detect if the dog escaped from the house, that's a binary classification problem. Is the dog present or not? And so that tolerates a much higher level of compression in my experience. So typically we need much bigger representations when we want very high levels of precision, and also it's a large multi-class problem, or the complexity of the data that we expect is going to be frequently changing. If we expect the data to be different tomorrow, but if we have a fairly standard problem, less classes, and we have a consistent idea, your garden's not going to look different tomorrow than it was today, so the dog will still look the same, we can tolerate much higher levels of compression. And I think that I'm hopeful that compression research is moving more towards baking in real-world constraints, because I think partly why we focus so much on kind of a narrow set of compression techniques is that we've really been focused on theoretical aspects of compression and not necessarily how it translates to hardware. So yes, I think it will continue. I think that the main question will be, do you create hardware dedicated for inference situations, which will have just baked in lower levels of precision? So you train with high precision and you deploy with much lower precision.
Thank you. Second question on top of the final takeaways. I clearly didn't know about the Anna Karenina principle, so I'm going to have to look it up. Looking at the winters of AI that we've seen in the past 50 years, it would seem to me that at least the two first winters are an indication that it's not a good thing to depend on one government or several governments for a specific breakthrough to continue on and so forth, to have the activity that it did. Mostly because, as you said, for the thinking machine, it took DARPA a moment of thoughts, and essentially the whole thing was wiped out in a matter of a year or two. So my question is, why do you think that the commercial use case that are being prioritized are essentially, look to me like they're not such a good thing? Because to me, they're essentially the savior of this whole thing. That is, I mean, I realize that somehow it's kind of difficult to get the hardware to be doing different things if somehow the primes are a bit in the same format somehow. But at the very least, if there is some concerns from the private sector to solve those primes, and you arrive with a technology that's kind of out there but solves that prime, you're in a much better shape to find the money to essentially get there than if you were to try to convince any DARPA manager to do so. What's your take on this?
Yeah, I mean, it's a fun question. I mean, what you're so as someone who's part of Google Brain, I have nothing against industry approaches. So I think that many of my colleagues are working on very interesting hardware approaches to this problem, and the more diversity in approaches, the better, as we all know. The tricky part, I think, is that it's a search space which is bound by the need to make money. And what that means is that most is focused on research ideas which already exist and making those work better with hardware, which is not a saturated space. There's still many low-hanging fruits there. It's very open because essentially we've done very little work there. How do we take all these algorithms we know are widely used and have a high impact and actually make them work? But it's a different question from asking, how do we anticipate the next leapfrog idea. And a good example of this is that, so yes, DARPA did cut down thinking machines, but Canada largely preserved their funding. So the US and the UK wound down their funding. Canada largely, for some reason, was very plucky and continued throughout. And if you notice, most of my directors, the senior researchers at Brain, they're all from Montreal and Toronto. All of them. And there's a reason for that, is that you need a sustained source which is not price sensitive. And that typically is government. And I think that we're lucky that we're in a very exciting time of commercial innovation. But I imagine that we will face, it's hard to know the counterfactual, but there is the lack of conversation about this at a national level can only hurt progress because it's so absent.
Okay, thank you, Sara.
Thank you. Other questions? Okay. Otherwise, yeah, there is one. Do you have a peculiar insight about bio-inspired hardware processors by Logan?
Yeah, I don't have a particular, but they're exciting to me. So the paper which I read, which I really enjoyed, came out recently. It's called Xenobots, and it's about how do you really try and do an architecture design algorithmically, and can you translate that to a cellular level? And what was interesting is that you have a lot of baked in priors to cells. So you have a lot more dynamic interaction between the architecture qualities that you want to codify and how the cells actually interact. But the research on this is fairly recent. A lot of it's coming out of one lab at MIT. So in many ways, the tricky part is what level of precision will we have over other units which we don't understand. So it's fascinating because we're almost trying to layer on an architecture onto a cellular unit, and we don't even really understand a cellular unit. So it's a very empirically driven exploration, I would say, because not only are we abstracting away the theory of the network itself, but we're abstracting away the theory of what we know about how cells will interact. And so I think it's a long time horizon. But for me, it is fascinating because one thing which is missing in current networks is ability to adapt to new tasks. And that, I think, in part is because we have this issue called catastrophic forgetting, where when we train on new data, we just overwrite the weights. And this problem really amounts to the nature of how we train, which is global updates. Global updates, by the way, is also why we will reach a limit in terms of how big we can train, because it's very difficult to do a global update. That's not how our brains work or how cells work together. It's not a global update, it's local signal. So I do think in that respect, it's much more fascinating because we need to move away from global updates. It's very clear there's a cliff there in terms of how big we can go. So thinking about innovative ways to do that is always interesting. But it is very pie in the sky right now. I think that's the phrase.
That's very fascinating. Other questions? Otherwise, I can finally ask mine. Yeah, I actually have two of them. One is just out of curiosity. You mentioned unstructured sparsity. Do you have like another favorite loser of the hardware lottery? More specific one?
So I do think one of the difficulties is so it's an idea, but I do think it's this idea that right now we treat all examples uniformly. So having more dynamic structures going forward where we can route examples and essentially treat examples differently during training will require different types of architectures. We won't do a full forward pass on a predetermined batch. The reason why this is interesting, is probably my favorite other hardware lottery loser, is that treating all examples equally is incredibly inefficient. If you think about it, it's almost like saying it is saying everything is equally important. But we know as humans that that's not true. Like often we squint when we see something important, we zoom in, but largely we ignore most information. So figuring out ways where we can have routing mechanisms and where we can have batches of different sizes, which currently is possible on things like GPUs, but not possible on TPUs. Having more flexibility in how we govern the input space is important. Oh, I do like that comment from Pierre. Yes, that sounds like an excellent paper title.
Yeah.
Yeah, precisely. It is a hard. It is in the vein of hard mining approach. Oh, it is actually a paper. Now I understand.
Okay.
Yeah.
Yeah. Then I have other two questions. So the second one is, do you think like setting very ambitious benchmark challenges, like for example, ImageNet or these kind of things, can be like a driving force of innovation, not only
Yes.
in software and models, but also hardware?
Yes. I do. So right now there's benchmarks like the MLPerf benchmarks, but I would love to see more hackathons that bring hardware specialists and researchers together that are more orientated towards open forum brainstorming, but then under some type of, we tried to do this. So we set up a workshop last year at Meetups where we were trying to do a compression, but expand the notion of what compression meant. So we really wanted to try and connect it more to hardware. And we had some great submissions, but even evaluating it was tricky, and we ended up doing a subset of the metrics that we wanted. But having more touch points where we start iterating on what metrics can we actually compare performance on all these different types of hardware? How can we get more hardware people and researchers in the same room with some type of purpose? I think that's very needed. And MLPerf is one version of that, but you almost abstract away the algorithm, because you're almost saying, we take the algorithm, let's try and see how fast we can go. So more dynamic competitions would be fun, where you're trying to, you have some type of algorithmic task and you're trying to make the hardware work for that. That would be fun.
Yeah, I looked at MLPerf some time ago, and there is an open track where you're allowed to change the algorithm.
Oh, good. Excellent.
But it's not very competitive. Like not many people are submitting there. So like the place exists, but it's not very well used.
Yeah, this is the tricky part, is if you don't have metrics to codify how you measure performance, it's not a good feature of scientific progress as well. People want to understand how they're doing. So too open as well is not good. So there needs to be a sweet spot.
Yeah, also there are different rules. It's a very long document explaining. I don't understand everything that's in it. So. But yeah, and finally, I have a last question that's more about like many things that you went over in the talk. Like you pointed to many different reasons why like going exploring outside of the beaten path is costly. But like in the first list you made, there wasn't really much focus on the cost of actually developing hardware, and then you kind of talked about it later. My question is, like, do you think like some of these reasons that you listed are more important, more challenging than others? And if you think so, like which ones?
Yeah, I mainly omitted that from the last slide because I'm also trying, ideally that is the most important, but it's also what's addressable. It's unclear to me that the cost of developing hardware or the iteration cycle is going to change dramatically, or the model for developing it is going to change dramatically in the medium term. I think in the long term, that's a different question. For the medium term, I think it's more likely that we first need to have a more informed opinion of why it should be different. And right now we don't. So right now, researchers, we just take what we're given, go about our day, submit to NeurIPS, continue. And I think that for me feels like the most critical part is that in order to advocate for different types of hardware, we need to have more data about why our current hardware isn't sufficient. And that needs feedback loops. So when I deploy something, I want to know even from a compiler level, what took profiling, what about my algorithm is slow. Right now, there's not even basic profiling tools. And you can, if you set up your workflow, you can obviously get at that, but it would, in our UI tools, we should have just better profiling tools at a hardware level all the way up through the software stack. And then the second thing, which I believe there was a question, maybe it was Logan who asked, but who was talking about this heterogeneous landscape. So that for me, I think is very interesting as a problem because that is the immediate pressing issue. So we will very quickly have many different types of hardware because there's many brilliant companies working on it. Like obviously something also that you're thinking about. But how do we then navigate this landscape and quickly experiment on different types of hardware? Because my algorithm may be well suited to a hardware that you develop. But if the cost of me testing it is high because of software incompatibilities, there's a huge inertia there. So that I see again as probably higher up, mainly because it's something I think we can fix in the medium term and invest in and think about.
Okay, great. Thanks for your answer. There is a question from Bogdan. What about spiky neural networks dedicated hardware? He's asking if it is a lottery ticket with a high chance to succeed. I'd say that's cheating, but.
So I have heard of some companies who are working on hardware that is very similar to spiky neural networks. I don't know how that's going for them. The tricky part about spiky neural networks is that even algorithmically, it hasn't proven to be empirically that promising, but part of this whole talk is suggesting that might be because of incompatibility with the hardware level. So I don't have an informed opinion. Does anyone here have a strong perspective on whether spiky neural networks are the way? Lottery tickets, I definitely think are quite exciting. So I can speak. So lottery tickets in their current form don't work at scale. In fact, you need a hack. So you need to train for a few epochs before you reset. But the theoretical motivation for lottery tickets is quite exciting, which is that can we find a distribution and then we have this distribution at the start. Why this is exciting is that if you have that, then you can just start with your sparse matrix baked in, and it changes the framework for how we need to think about the hardware level. So that I think is very promising. And the question becomes, can we get at this distribution of weights? And so far, this is a very active research area. So I'm hopeful that there's going to be interesting ideas this year. Last year, there was many different improvements, but we're still not there. There's still a lot of assumptions that need to be made.
Yeah, I share the fascination for lottery tickets.
Yeah. Because it also allows you to possibly go big early. If you can start sparse, you can start with a very different, you can grow bigger over time, possibly, which is a different variation of this.
Yeah, and also like there was this work by David Hai and Adam Geyer last year.
Oh, hypernetworks.
No, it was the networks without training where they were just doing these small weight agnostic neural networks. Yeah. Thanks, Julia.
That was it, yeah.
And yeah, we had Adam at a previous meetup, and he was saying that he had to run the thing on many CPUs, and it was like not really efficient to run. And like I think it is somehow connected, maybe connected to lottery tickets, but it shares the same like deficiency of not being like very well designed for current hardware.
Yeah, I agree. I agree.
Are there any other questions?
Yeah, to circle back to the question I wanted to ask before, but I let some time too, because I think it's more of a discussion. And actually, you brought it up in your answers. It's in a way, kind of the question on the discussion is, you brought it up with local updates, because when you look at how we do training of neural networks, when you look a bit about it kind of out of the box, like not just backpropagation, you realize it's a bit dumb, and it's a bit not suited to hardware. Actually, if you look at distributed systems, the fact that you have backpropagations means you have communication in this system, and it's not really a good thing. So in a way, I wanted to ask you that, is that, could it be like, could we use alternative training methods other than backpropagation to kind of rig the hardware lottery, to change it, and to maybe favor different type of hardware, or maybe inform the design of hardware?
Yeah, I agree with the question. I mean, it's something I'm currently working on through the lens of thinking about how do we treat capacity differently. So right now we have these massive neural networks, and a lot of my recent work has been showing that when you compress, you lose performance on the small subset of data points. And these data points are much more challenging. They're more atypical, they tend to be noisy. What this finding says differently is that most of the capacity in a network is being used to encode a representation for the long tail, the low frequency data points of the distribution. And this is not a good use of capacity. In many ways, it's got me thinking again about this difficulty of doing global updates, but also of treating all examples equally. And for both, you're constrained. So even if you do distributed, yes, you consolidate your updates, but also then the data that you do updates on becomes far more important, because you don't have a good understanding of what data is important and what is not. So the lens that I see this in is, one, yes, there's various questions that are interesting right now about modularity. So can you constrain parts of the network to do different roles? There's other interesting questions about, can you just use networks differently? So can you have much more of almost thinking about cascading type models. So certain parts of the network are used for certain types of examples, and other parts are used for different. This constrains the size of your local update, of your global update at least. But there's a wider perspective, which is that you get at this when you talk about distributed, which is that even as humans, a lot of our intelligence is not individual, it's collective. So we're very good at, we have shared understandings of time and symbolism and myths that allows us to collaborate in ways which we wouldn't achieve alone. And there's a sense with networks that we have this singular vision of a single network that solves everything. And that's far from clear in my mind if that's the way that we need to do this. It seems much more promising to think of essentially a series of networks that exchange updates in different ways. But what that looks like is an open question. I think it is going to receive a lot more attention. The beauty of the beginning of a plateau in research breakthroughs is that people start experimenting more. So we've just had a decade of people kind of in a feast mode. We had deep neural networks. Everyone, there's no reason to diversify because there's so many things to discover here. We're at the feast table. And now there's been a plateau in breakthroughs. And that's always when people are willing to diversify much more their research portfolio. And that, for me, is very exciting because these are things I've been grumpy about for a while, and I think that now there's more impetus and interest in addressing them, that we should think differently about some of these things and assumptions.
Yeah, so thanks for sharing this. It's very interesting. We have a similar reflection actually around this, which was in part I think sparked by your hardware lottery paper. Like we have actually we have at New Apes next week we have an all at the Beyond Backpropagation workshop where we talk about using like alternative training methods, and one of the slides in the talk is about using alternative training method to rig the hardware lottery to get out of it.
Interesting.
And, it's very interesting. I think that your view is more focused on changing the model actually, because you say changing it a lot by like putting it into small parts that could cooperate between one another. I think it's a very interesting view that I kind of missed personally before. In our view, what we are kind of arguing is we are saying that maybe just you don't necessarily have to change the models because they work well. Like we know transformers, attention, we know these are great ideas. Maybe but if you change the training, just the training, so just not doing backprop, but something else, and there is a lot and a lot of literature on this, and an increasing amount actually, an increasing interest in that maybe you can fundamentally change the trade-off. And I think the biggest example is the one you said, it's local updates. As soon as you have local updates, you change everything. And suddenly training like a 1 trillion or 10 trillion parameter network is not impossible anymore. It's actually something that is relatively easy suddenly if you have the resources, which I think is fascinating.
Yeah, I don't think they're contradictory. So I think that approach is also very valuable. My approach is in part informed by the second challenge, which is task adaptivity. So a lot of my research is on also robustness. And it seems clear to me that so within a network, it's very interesting to do local updates and see if you can fulfill the task in mind. But if you are doing task adaptivity to multiple tasks, you may want to also have multiple networks, just because we know that there's huge issues with catastrophic forgetting. So I think both are particularly at this stage of research, I think both these approaches are very valid. And it's very interesting. I must catch that talk next week because it sounds fascinating.
Sure, yeah, sure. We'll be happy to have you at this workshop, and if you come, it would be very nice. But yes, thanks a lot. And I think it's very interesting, and this was a lot of good points and a good learning experience. Thanks.
Thank you for the answer. And there is a last question by Pierre, for which I can partially answer. I think there is any chance you know a TensorFlow implementation of local updates. I can say we implemented a method that does kind of local updates in PyTorch, and you can go on the GitHub of LightOn. We can point it out to you. But yeah, Sara, if you know of any other.
Oh, no, go for it.
Yeah, in general, I find that like some local updates methods are quite hard to implement either in TensorFlow or in PyTorch, and like they're not the same set. Like some methods are very well suited to TensorFlow and some to PyTorch for the way they work. But like local updates is a very wide term, so yeah.
Yeah, and I want to say something on this, which is that it's definitely a case when you mention hardware lottery or even like the software having an influence. It's definitely a case where alternative training methods are hurt in a way, because
Yes.
a lot of these libraries are built with backpropagation in mind.
Yes.
As soon as you want to do something else, well, firstly, there is you kind of go into a weird territory, but also in terms of performance, because often we motivate these alternative training methods by saying, oh, there are potentially, local updates faster, blah, blah, blah. But then you implement it and you're like, well, why is it not faster? It should be like my complexity should be lower. But you realize that there is so much stuff in the library, in the engine that is built for backpropagation. And it's a huge like technical depth in a way, and it's a form of lottery as well, I think.
Yeah, I completely agree.
Okay.
Sara, I'm curious. I'm sorry for the stupid question. At some point, you mentioned $165 million for doing new hardware. Where does does this figure come from?
I cite it in the paper. I believe it's a report on hardware development, but there are a few figures, there are a few data points in the report about the cost of iteration. One is the length of time, which I believe was from a report by Jeff Dean, which is 2 or 3 years. And then the 165, I think is cited from a different report, but it should be in the citations.
Cool, I'll check it out. Thank you.
Yeah, does that, I'm curious, is that high or low for you?
No, it's pretty standard. I mean, we're a hardware company, so we're raising funds and everything. And so that figure doesn't come out to be too high or too low. It's actually pretty average. It goes, I think GraphCore right now has raised about about $450 million so far.
Mm-hmm.
And so they're getting into coming out with cards and everything. I think there are 2 or 3 other companies that are in the 100 plus million raised so far. So to me, it looks like it's indeed a good average. I mean, it's not like that there are that many hardware companies either. So whatever average we do on 4 numbers is really meaningless somehow. But no, I was kind of wondering if somehow there was a point I had not seen
a
before.
repository.
So, no,
Yeah.
I check out the reference.
Yeah,
to see
please
how it's,
do. There's also, I believe there's a report by Neil Thompson. He's at MIT, and he also does an interesting paper which might have relevance to you, where he does talk about the economics of hardware companies a little bit, I believe,
Sure.
in the first part.
Okay, cool. Thank you, Sarah.
Thank you. I'd say we can close here. It's already 1 hour and a half almost, and I guess Sara has other things to do. And it was great having you. Very
Thank
nice
you so much.
presentation, great discussion, and like really useful for us. So yeah, I'm gonna put the video of the meetup on YouTube, on our YouTube channel later. And well, have a nice day.
Yeah, lovely. Thank you so much for the invitation, and a very good discussion. I enjoyed it a lot.